Hi guys, today's video is about dividing polynomials. So we've done addition, subtraction, multiplication, we're left with division. So before we jump into dividing polynomials, we are going to review long division with integers. It's probably been a while since you've had to do something like this. So say I give you this problem, 714 divided by 4. That's the same thing as 714 divided by 4. It's also the same thing as 4 on the outside, 7, 14. So usually I know what you would do right now is you'd plug this into your calculator, figure out what it is, and you'd walk away with a nice decimal. We are going to review long division because we can't use our calculators to do long division of polynomials. So let's run through a brief review of this. So if I am dividing by 4, then I first see how many times 4 goes into 7. 4 goes into 7 one time. Then I do 4 times 1, which is 4. And then I subtract 7 minus 4 is 3. Then I bring this 1 down. Then I say, okay, how many times does 4 go into 31? That's 7 times. 7 times 4 is 28. Subtract those. I get 3. Ooh, sorry, the arrow's all weird. Bring down the 4, and then ask how many times does 4 go into 34? Well, 4 goes into 34 8 times. And then 8 times 4 is 32. Subtract those, and I'm left with a remainder of 2. So we would say the answer, or the quotient here, is 178 remainder 2. Now I want to talk about another way to write your remainder, which is going to be really important for dividing polynomials. So I like to think about the remainder as the stuff that didn't get divided. So we divided 714 by 4, and we got 178. And we have 2 left over, which means that the 2 still needs to be divided by 4. So another way to write this answer, this quotient, is that when you divide 714 by 4, you get 178, plus you still need to divide that 2 by 4, right? So this is also like saying 178 and a half, or 178.5. So if you put that in your calculator, that's what you would have gotten. So that's just one way of looking at the remainder, and this is going to be really critical as we move forward to division with polynomials. Okay, so let's do an example with polynomials. Like we discussed at the very beginning of all this unit, polynomials behave very similarly to integers. So when we look at doing division with polynomials, it's actually going to look super similar to division with integers. It's just going to have some variables in it. So let's do this division problem. X squared plus 3x plus 7 all over x minus 1. Okay, we're going to set it up the same way. I'm going to scroll down just a bit. We're going to set up the division the same way. So I'm going to have x minus 1 right here. Then I'm going to put the x squared plus 3x plus 7 in here. And now we're going to go about the same process. So I want to look at this x minus 1, and I want to know how many times it goes into x squared. Another way to think about this is, what do I multiply x minus 1 by so that it's really similar to x squared? The answer to that is x. So if I multiply x times x minus 1, let's write that out really fast, x times x minus 1, that is going to give me x squared minus x. I'm going to put that answer right there. Just like how up here we took let me put on my highlighter so you guys can actually follow what I'm saying. Just like how we took this 1, multiplied it by the 4, and then put that 4 right there. Okay. The next step is subtracting, just like we did above. So we're going to say, okay, what's x squared minus x squared? Well, that's 0. What's 3x minus a negative x? Well, that's the same as 3x plus x, which is a positive 4x. Okay, I'm going to scroll down a little bit. Now we're going to bring down our next term. So now we're going to have 4x plus 7. Now we're going to go back and do the same thing. What do I multiply x minus 1 by so that it gets really close to 4x? The answer to that is 4. So if I do 4 times x minus 1, put that answer right here, I'm going to get 4x minus 4. right? Now I'm going to subtract these. So the 0 we can just ignore because it's 0. We have the 4x minus 4x, which gives us 0. And then we have the 7 minus a negative 4, which is the same as 7 plus 4. So I'm left with a remainder of 11. I made it to the end of my polynomial. I've divided everything out. So now it's time to write the quotient and express the remainder. So the quotient that I got is x plus 4 is what you get when you divide x squared plus 3x plus 7 by x minus 1. And I still have this remainder. So I'm going to write it as just a remainder 11 right now. Now a better way to write this would be to say, okay, I divided it, I got x plus 4, but I still have this extra 11 that still needs to be divided by x minus 1. Don't really have a way of doing that division, but I know that this is true. So this box that I just boxed in is actually the exact same statement as right here. I'm going to kind of draw a line connecting them. So this fraction that we started with, the big fraction, let me get my highlighter out again. So this big fraction that we started with up here, we were able to make it look a little bit simpler by doing the division and then coming all the way down here. Okay? So one of the reasons this is nice is that when we started, we had a giant fraction. We didn't really know what to do with it, and it was kind of complicated. After division, we have a pretty simple polynomial, and then a somewhat messy, but still pretty simple fraction right there. So long division of polynomials might be complicated to do, but it really gets your expression looking a lot nicer than when it started. Okay, let's do one more example. Hopefully I left myself enough room to do it down here. So we are going to do this one, x cubed plus x plus 1 times x plus 2. One thing before I do this example, I know that this kind of fraction of polynomials, you have a polynomial on the top and a polynomial on the bottom, can be kind of scary to look at. I want you guys to recognize that it's not scary. We know how to deal with it, and we're going to spend a lot of time talking about this kind of setup. So get used to it because it's going to be awesome. It's going to lead us to some pretty cool stuff too. So one thing that is different about this problem than the last one that I really want to point out is that we are missing a power of x in the numerator. We jump from a power of 3 to a power of x to the first. We're totally missing the x squared power. And that's fine. It's not going to mess us up or anything. But we do need to take a couple extra steps to make sure that we take care of that x squared. So I'm going to write out the division just like we had before, but I'm actually going to add something. I am going to add in here a plus 0x squared. Now, adding 0x squared is just like adding 0, so it's not going to change the value of the polynomial, and it basically is acting like a placeholder. Whoops. So it's acting like a placeholder, and that's going to allow us to get a quotient that's actually accurate. And I'll show you why that's important in a second. So let's do our first step. So I want to know, what do I multiply x plus 2 by to get x cubed? And that's going to be x squared. So I multiply x squared times x plus 2. Then I'm going to get x cubed plus 2x squared. So I put that. Okay, let's pause right here. This is why it's important that I put in a placeholder. So if I didn't have this 0x squared here, I wouldn't have anywhere to put my x squared, or anywhere to put 2x squared. So that's why it's so important that we kind of fill in the gaps of whatever powers are missing. Just because the power is missing in the original polynomial doesn't mean that it's going to be missing in the quotient or the answer to our division problem. Okay, let's get back to this then. So we multiplied x squared by x plus 2, and now we're subtracting. So x cubed minus x cubed is 0. 0x squared minus 2x squared is negative 2x squared. Okay. Now let's bring down this x. Now I have to ask myself the same question. What do I multiply x plus 2 by so that I get 2x squared plus x? And I'm going to multiply x squared by 2x. The real idea here is when you're choosing what to put on the top up here as part of your answer, you want to kind of match up the powers of x. So if I multiply 2x times x plus 2, I'm going to make it, oh, I actually need it to be a negative 2x, huh? That is my bad. Let's do some erasing. So I need, okay, I actually want to multiply this by a negative 2x squared because I want this first term right here to match up completely so that when I subtract, it goes away. We'll see what that looks like now. So if I have 2x squared minus a negative 2x squared, then I'm getting 0. Now if I had a 2x squared minus a positive 2x squared like I had originally, I would have another number here. And then it's just going to get messier and messier. The idea is that I want to get rid of this whole first term. Okay, what am I missing? Okay, x minus a negative 4x, which is the same as x plus 4x. So I get a 5x. Okay. Now I say what? Oh, and now I've got to bring down a term. I'm getting all sorts of jumbled up here. It's a long process, but it's not too bad. What do I multiply x by to get me 5x plus 1? If I multiply x plus 2 by 5, I'm going to get pretty close. So let's do 5 times x plus 2. I'll throw that right here. 5x plus 10. Then I'm going to subtract. So I get 5x minus 5x, which is 0. 1 minus 10, which is negative 9. And then that is my new remainder. Okay, so I'd write the quotient for this as x squared minus 2x plus 5 plus negative 9 over x plus 2. And that would be the quotient. So this part right here, this term, that's really the remainder. That's what's representing the remainder when I do the division. Okay?